Hello and welcome to TWSS 2023. We'll go ahead and get started for today. My name is Colleen Dunn. I am the sales coordinator here at TechX Corporation. Welcome back to day 2 of our annual user conference. Our first presenter today is Dr. Dan Faircloth. Dan Faircloth was born in Cambridge in 1974. He received his PhD in high voltage electrical engineering from the University of Manchester Institute of Science and Technology in 2000. In 1999, he had joined the National Grid Research Laboratory in Surrey, UK, where he ran research projects into online condition monitoring, intelligent data analysis, and explosive failure of porcelain-clad bushings. In 2002, he joined the ICIS Neutron Source Rutherford Appleton Laboratory, Harwell, UK, where he was involved in caseated high current negative pending ion source development. 2014, he formed the Low Energy Beams Group, ICIS Neutron, and Nuances, the Rutherford Appleton Laboratory. This group delivers beam for ICIS 24/7 operations, operates 4 accelerator test stands, and has extensive expertise in high voltage engineering, RF, vacuum modeling, large-scale simulations, accelerator technology, and plasma physics. He has collaborated with CERN, Fermilab, Batavia, Illinois, in the US, SNS Oak Ridge, the Los Alamos National Laboratory, the Chinese Academy of Sciences, IPP Garching. Wow, Dan, a lot of places and universities all over the world. He teaches at the CERN Accelerator School in Cockcroft Institute and the Johns Adams Institute. That is an amazing introduction. We are so excited to have you, Dan. And on that note, I will let you take over. Go ahead and share your screen.
Thank you, Colleen, and thank you for this great honor to talk at one of the TechX World Simulation Summits. Yes, so good morning, afternoon, good evening, everybody, wherever you are. I'm going to give, this is basically the talk I gave at the recent Ion Source conference in Vancouver last month. It was held in Victoria, rather than Vancouver, on September the 18th. And it's about something that we've long held close to our hearts in the ion source community, the Child Langmuir equation and the Child Langmuir effect. And it'll be interesting to see how much everyone else knows about this. I'm sure probably everyone has heard about this. It's named after Child and Langmuir, 2 Americans, 100 years ago, came up with the theory of space charge limited extraction. And they were looking at the charge, the electrons being extracted from hot filament, an electron-emitting material. And they came up with this equation that defines the current density that you can extract from an electron-emitting surface. And how it works, the thing that's limiting it is the space charge of the beam itself. So you apply a voltage between the anode and the cathode, and that creates an electric field on the surface, the emission field, and that causes the electrons to start being pulled out. And as the electrons are pulled out, they have their own charge, their own Q. And that charge, that space charge, cancels out the electric field. And you eventually get to this self-limiting, this space charge limiting maximum current, where you can't pull any more current out of the surface. If you solve the equations, you get this V to the 3/2 dependency of the current that you extract from an electron gun is dependent on V to the 3/2. Now, this formulation of this equation is one-dimensional, and they never intended it for it to be applied to ion sources. They only ever intended this to be applied for electron emission. So I'm not saying Child Langmuir effect is wrong. It's just that how we've been applying it to ion sources for the last decades is wrong. And as you'll see, it's just an illusion. There's no V to the 3/2 dependency from when you vary the extraction voltage on a single voltage sweep. Oh, this is what, sorry, I wondered why this didn't do this. This is why I paused earlier. I thought I'd put this animation, but there's the animation of it in. I thought I'd added that in for you. But we've just talked this through anyway. So the assumptions, there are these six assumptions really for the Child Langmuir equation to be true. And for these are all pretty much true for ion sources, for electron guns, but for ion sources, there are not infinitely many particles available to be emitted. The particles do not have zero initial velocity. One good thing for at least they're non-relativistic in ion sources. They're definitely not yet relativistic. The electrodes are not infinite. There is not a constant spatial distribution of particles perpendicular to the direction of the beam propagation, and there is not a zero electric field at the emitting surface. However, even with all that stuff, we've been going on about this for ages. This is the accepted wisdom that ion sources, there's two regions on a voltage, extraction voltage. Sorry, I'll get a better pointer up. Let's pointer options. Laser pointer, that's a bit better. As you vary the extraction voltage, the current goes up. And this bit at the front, where it goes up, we like to fit V/3/2 curves to this bit, and we call this the space charge limited region. And then eventually you get to this bit that is emission limited, the perviance limit, where you can't get any more beam out of the plasma, we like to say. And here's three different cases of of a high plasma density, a medium plasma density, and a low plasma density, but they all have this rise at the front. And this is in books. And in fact, if anyone's been to any of the CERN accelerator schools, I've been talking about this for the last decade as well. I put these graphs up and talk about V⁵. So yeah, there is our dogma that in the space charge limited region, the extracted current varies of V/3². And as I said, I am guilty of putting these V/3² curves. There at NIBS is a recent example, the negative ion beam conference. Look, there are published a nice V⁵ fit. There we go. There's at ISIS a bit longer ago. But again, there I am fitting a V⁵ curve to my data. However, the true cause of this observed power law is not space charge limited extraction. It's meniscus focusing and then collimation on the extraction electrode, on the puller electrode. And we've recently done some work with the University of Uvascular to prove this. And we published this year, just in July this year, in Plasma Sources, Science and Technology. And basically we did some experiments and we did some modeling, and they pretty much confirm that the observed power laws is caused by meniscus focusing and collimation. I'll just give you a brief summary of the experiments. So it was a very simple ion source. It's a filament-driven hot filament arc discharge plasma, and it's an argon plasma to keep the chemistry as simple as possible. Single hole extraction, and then a gridded extraction. So instead of a hole, we had a grid. So that's pretty close to trying to deliver on an infinite parallel plane extraction. That's as good as we can get. And then underneath that, the Faraday cup for measuring the Faraday cup, we had a segmented Faraday cup. So you can measure the you've got a very good fundamental measurement of the divergence of the beam. And you can see here the beam, as it hits as you vary the voltage, the beam gets larger and smaller as it's focused, as the beam is focused smaller as you increase the extraction voltage. And if you add up all those segmented things, there's no V⁵ law there for the currents. So experimentally, we didn't see this V⁵ when we looked really closely, and we wanted to model this. Now, how do you model beam extraction from plasma? There's two options, really. There's PIC codes, VSim, and then there's all the ones that the universities and various collaborations and people have developed over the years as well. But the problem has been to model the meniscus, you need to resolve the Debye length, because it's the Debye length feature. So to do that, for reasonable plasma densities, you need a tiny mesh density. But then we go and extract over, say, 10 millimeters or 20 millimeters. And to maintain that mesh density over that distance is impossible. It's not computationally tractable. Well, up until recently, it hasn't been computationally tractable. Or the other option is gun codes. These are plasma equations coupled with tracking codes, and VSim I recommend is developed by University of Uvascular and is open source, but there's commercial ones, iGun. But the problem with this is these gun codes is, do they really reproduce the plasma dynamics properly? Or there's the combined approach, and this was recently done by us in our paper that we published earlier this year. This was what we did the previous year, where you have a tiny little region where you model the plasma, and then you model the meniscus and a bit of the propagation. You then pass the particles on the boundaries to a tracking code and track them across the rest of the gap. And previously, you've run your electrostatic gun code to work out what the boundary conditions were on your particle and cell model. So this requires passing between models, but it does work, and it works very well. We got really good comparison when we used VSim and IBSimu to do the tracking. You can see the positions of the meniscuses for three different extraction voltages here. They're very close. They both predicted pretty nice jobs on the position of the meniscus. And you can see the experimental results match very nicely with the IBSimu, pure IBSimu, and the IBSimu VSim combination. But the problem is that there's still doubts with that, really, isn't there? Because when you're combining models, how do the models interact? And you've got to transfer the boundary conditions. How many times round you iterate the boundary conditions to be sure you're right? So, but thankfully, in the VSim from the latest VSim 12 and I think VSim 11 anyway, when it started in axisymmetric, you can have a variable mesh density, which is one of VSim's absolute killer apps, as it were. It's your USPs. It's brilliant. No one else can do a variable mesh. And that's allowed us to model the entire extraction, plasma, meniscus, and tracking in a 2D3V cylindrical symmetric model. And we basically had it's a cylindrical symmetric. So we had our plasma electrode, we had our plasma production region where we were literally just birthing argon plus one ions and electrons at a birthing rate. And this was the only variable in the whole model. This was the only knob. You could vary the rate at which we birth particles. And what we did is that for a 4 kV extraction voltage, that is the voltage where all the beam goes through the extraction electrode, the puller electrode, and you measures on the Faraday cup. And we use that as the point where we then set the load density in the model so that the beam current we measured matched the beam current that we measured in the pit model matched the experimental. And then we varied the extraction voltage. So there's the mesh, a very aggressive change, but a smoothly aggressive change. But that allowed us to get the plasma and the post gap, the acceleration gap, the extraction gap, measured resolved in 383 by 448 mesh cells. So we basically just ran it. There's the argon ions at the top and the electrons at the bottom. And there's 3 kV example here. And we ran it until it converged, until it stabilized. So ran to equilibrium. And that was by about 25 microseconds in the model. That took about 16 weeks on a 32 core machine. But the electron energy distribution function was nicely resolved. You can see that it's about just under 1 volt plasma potential, and you can see that little peak there on the electron energy distribution as the electrons are accelerated to the wall of the plasma chamber there. Anyway, we ran this for loads of different extraction voltages and recorded the total current, the beam current, and the emittance after the extraction electrode. And here's the results. So for 500 volts, so we've got the top are the argon ions, and at the bottom is the electron density. Here's the currents. The blue is the total current emitted through the plasma electrode hole, and then the red is the beam current as measured on the back of the model there, as it's got through the extraction electrode. And then down here is the emittance. And you can see as you increase the extraction voltage, the electrons are pushed back into the plasma chamber. The meniscus, this is the emission surface where the argon ions are essentially turned into a beam from the plasma, is pushed back 2 kV, 3 kV. We're now starting to get this S-ing, which we'll talk about in a moment, on the beam emittance. But 4 kV was our matched case. 6 kV is now over focused, and 8 kV we're out the other side, now completely over focused, and the meniscus is pretty much into the plasma production region. There's the data. That is our experimental data. Very nice measure comparison between the experimental data. There's the VSim, so the gun code data. Pretty good. That matches very nicely as well. You try and fit a V/3 to the curve to that. If you squint and look sideways and hope for the best, you can, which is what I did all over these years, but there shouldn't be a V/3/2 curve there, really. It doesn't fit. So how do you measure a true perviance plot? You can either, in the simulations, it's easier in that you just look for, you'd have to get the constant meniscus at each plasma, at each extraction voltage. You would need to vary the plasma density. But again, the plasma density is then different, so that's not quite a true perviance plot. Experimentally, you could look again, you could try and measure the point where it starts hitting the extraction electrode. So this is the current on the extraction electrode. So you could say that point there is the matched point, and therefore what you would put the V/3/2 curve on if you really wanted to fit one to it. Okay, so moving swiftly on, as I know I've only got 9 minutes left. But just looking at the emittance phase space S shape, we've got really lovely evidence now for what causes that S in the phase space. If we look at, again, this is just exactly the same results. This is at 500, 700 volts extraction voltage. You can see here's the electrons bulging out the meniscus. But if you look at now we're plotting here the radial velocity, and that is what really defines the emittance of a beam. It's how much the velocity outwards, be it X and Y or radial or whatever, the radial ion velocity is the emittance. And you can see it's got quite a high positive radial ion velocity here. So because it's divergent, the beam's very divergent. But as we increase it, what happens is very interesting. Here, this is the point it starts to happen. When the meniscus comes inside the plasma electrode, the corner of the hole, the outside hole of the plasma electrode, you can see the sharp pointy corner of it. And that creates, as you can see here, a blue on the bottom here, the radial electric field. It starts to reveal itself. And that radial electric field is what gives the beam, you can see here, blue, a strong radial kick. And the emittance has just jumped up as well here, because you can just begin to see the start of this S. They're very faint, but that becomes more clear. There's the S. And you can see the larger field here on the outside edge has been revealed. More kicking down of the more S-ing is caused by this. The particles that are emitted from this part of the meniscus, they see a strong radial field and give it a real S shape to your emittance plot. And there we go, carrying right on 6 and then 8 kV. And in fact, looking at it with no plasma, with the really high extraction fields, it's the field is basically the same as if there was no plasma there at all. The emittances match pretty well between VSim and the gun code. They at least follow the same sort of shape. The numbers are a little different, but not a million miles away. The temperatures, this is going back to one of the assumptions, emitted with constant temperature, zero velocity. Not only are they not emitted with zero velocity, as you increase the extraction voltage, that meniscus eats into the ambipolar expansion from the plasma production region. And so the particles are emitted at different ion temperatures as it eats into the ambipolar expansion of the ions, which is going up and down in the extraction voltage there, because it's quite a nice little picture of it, of how the meniscus is pushed back into the plasma expansion region. I tried varying the plasma density. This is just an interesting point, that on this rising edge, it's very sensitive to the plasma density. And in fact, as you increase the plasma density at 2.3 kV, because it causes the meniscus to bulge out, your then beam is more defocused and you're losing more on the extraction electrode. And so as you increase the plasma density, the beam current actually goes down. The beam current drops and drops because the beam is going further and further out. And you can just see these points here with them varying. That as you increase the plasma density down here, the beam current drops. Whereas up here, as you imagine, the plasma density increases the beam current. The limit of 2D, so I'm hoping, so this was run on 32 cores, and I haven't yet got my models to scale onto we've got 4,500 licensed cores. I'm hoping to be able to reach the higher current densities that will allow us to get milliamp, tens of milliamp beam classes, because obviously we're interested in, say, 50 milliamp beams. I am almost finished. There we go. I'm just going to show the variable mesh, which is now up and running. And then 3D, we've got a 3D model up and running as well, because I want to look at negative extraction, which is going to require magnetic fields and dumping of electrons. So in summary, the front end bit of these voltage current plots in ion source is not the Child Langmuir charge limited extraction region. It's the divergence limited region. Now, I didn't get a chance to show these at ISIS, but I did have some. Oh, we're hiring. Quick job advert. If anyone wants to come and work for us, email me and I will. Yeah, we would love you to come and work for us. We've got 2 positions open at the moment. I am open for questions as well, a couple of minutes, but I wanted to show you these videos because I didn't get to show these. What happens at low extraction voltages? I worry about if these are physical, because the Debye length is not fully resolved in the gap. But I get these beautiful movies. At the top is the electrons, is the argon ions, and at the bottom is the electrons. And at 0 extraction voltage, the plasma, it seems to be blowing bubbles. It's blowing low temperature bubbles into the extraction gap with 0 extraction voltage. I'd like to hope this is maybe physical, but it could be because of a Debye length resolution problem. And I know that things do tend to blow up once you don't resolve the Debye length. And here it is with 100 volts. 100 volts is essentially suppressing the electrons back a bit, but it still tries to blow bubbles, which is very sweet. It still blows these little rainbow bubbles of cold ions. Poof, there they go. And I didn't show this at the conference, and I'm glad, but here we are amongst PIC friends, so you can maybe tell me that is non-physical. But yes, thank you very much. I am open to questions.
Yeah, it looks like we have a few. And if anyone has questions, you can type into the Q&A box on the bottom of your screen.
Oh, okay. Shall I answer those? I see.
Yeah, I can, and I'll, if you want, or I can read them to you. It's up to you, whatever's easiest.
Okay.
But, so the audience, so I'll do the first one. It just says, does your extracted space charge screens applied voltage? If it does, you get CL law.
Does your space charge screen the applied voltage? Yeah, it does. But yeah, if you don't get Child Langmuir, because at 0 extraction volts you still have a current, so there's no Child Langmuir really from plasma extraction. And then there's a second one again from Igor. Have you tried using Pierce focusing electrodes to remove the S shape? So in practice, yes, we have, but I am still, so we built Pierce electrodes for our penning negative minus source, and we did improve the emittance, and we did have problems with overheating electrodes because of the electron current. I haven't yet tried it. I've got a whole load of things I want to try with the PIC model, and that is going to be one of them. I want to shape the plasma electrode. I want to try all this stuff. So it's going to be very interesting to look at. And then Joseph says, thank you. And you, oh, sorry, Colin.
He said, thank you for the amazing presentation. And you are in Istanbul and being so gracious, but we have a whole crew of people here in Colorado that have really enjoyed this. And we've been on mute, so you haven't heard it, but this has been a fantastic presentation. And so there were some.
Oh, glad you enjoyed. Good.
It is nice to see this presentation. Do you think Pierce geometry and rounding the edge of the PE could eliminate the S shape of the emittance?
Yes, I think it will have a good effect. But what is so interesting is, as whatever shape you've got, and I want to try a 45-degree angle on the outside of the plasma electrode. I want to try a curve, and I want to try a Pierce angle on there as well. It's going to be, because you can't, what happens is, as the meniscus recedes inside the plasma chamber, the electrodes are revealed, and so whatever electrode shape you've got there is going to cause if it's got some tangential field, it's going to create some focusing, which will affect the emittance. Now, if you design your ion source to only work at one extraction voltage, then you can design whatever you like. But as is shown, if you try varying that extraction voltage, that the root point of the meniscus will just work its way round whatever shape you've got. You've made the exterior geometry of your plasma electrode shape. So yes, it's really interesting. I'm looking forward to experimenting with different geometries, if it can be optimized in different ways.
Let's do
and then
a couple of questions, please.
John Kerry wants to ask.
I want to ask you some questions
directly. So
first of all,
okay, John.
Yeah, first of all, wonderful talk. Really enjoy it. It's always been great to work with you over the years. So what's your maximum grid variation, and how many iterations did the Poisson solver take to converge?
It was quite a brutal grid variation, actually, there, John. I wanted to go as brutal as I actually possibly could. Like, I wanted it to be more brutal, actually. I wanted to go over a couple of orders of magnitude. So yeah, it's going over 4 microns to 500 microns. So that's going over. Yeah, it's going over 2 orders of magnitude, the change in the mesh density there. Yeah, and how many iterations did that take to solve? This was running on VSim. I think this was doing on. Was this running on 12? I think it was running on version 12. I'd have to have a look, John. I'll email you, but I think it was to tens, 100, something like that. I think I'll have to have a look.
We noticed that when we get more grid variation, the convergence, number of iterations to convergence goes up. So I'm curious to see what you're experiencing. But still, even at 100, if you have a large number of particles per cell, it tends to be small compared to the particle mode. Is that still true for you?
Yes, yeah. So to get to the plasma densities that I'm trying to get to, which is what I'm targeting, the really high plasma densities, you've got so many particles to get the statistics in the electric field. Yes, I've got the particle push step is still a significant chunk of the solve each step.
Great. I've just got 2 more things, and I promise I'm not going to take too much of my privileged position here to keep asking you questions, because we can always communicate later. But yes, very much to the new decomp. When you get 12.2.1, you're going to be able to improve your speed much faster because of the particle load balancing, which the guys here have worked hard on getting. So I look forward to your experience with it.
Yes.
Second, the knee and the transition that you see, you have a lower part where it slopes up, then you have a part where you are space charged. If I were to believe the red curves and the red dots, can we remove that Q&A or move it aside? If I were to believe the red,
there you go. There you go.
there we go. So the red dots, if I were to believe those for the beam, then the lower part where it's coming up almost parabolically, I don't know what that regime is, but the next regime where it shoots up real fast, that's of course space charge limited. And then over on the right, you're getting into the emission limited regime, right? Because when you put more voltage on it, you can't get any more. So that means you're probably emission limited. At least that's what we find in another case. So that's the preface to this question, which is that if the knee is the transition from space charge limited to emission limited, couldn't you look for it by saying, hey, where is my current equal to my birthing rate? I love the birthing rate term, by the way.
Or whatever you call it, the emission, yes, yeah.
I don't know the emission rate, but the birthing rate's nice. Gives it a human character.
But there is no Child Langmuir. It doesn't seem to be space charge limited. This is the emission divergence limited. It is because the beam is so divergent because of the highly prolapsed meniscus, the highly convex meniscus, that you then collimate it all. And so this front bit here is not Child Langmuir. This front bit here is focusing, meniscus focusing and collimation on the puller, this bit here. And even if you were to do it with full grid extraction, you can extract everything, you still don't see any V to the 3/2. There's no Child Langmuir on the plasma, not in this regime anyway, not in this ion source currents and densities.
Okay, thank you very much. It was a very inspirational talk, which caused me to think about this problem a lot more. So thanks again.
Yeah.
Pleasure, and thank you for having me. And I'm happy to talk to anybody, email me, whatever, set up meetings. And I'm really looking forward to carrying on this work with TechX. We've got a lot of great stuff coming up in front of us. I'm very excited.
Hey, Dan, this is Seth Weitzer. I just had a really quick question for you. How are you defining the edge of the meniscus? Is that some small percentage of the average plasma density, or is that 2 sigma from the density?
So there's beautiful. How am I defining the meniscus? As in, how am I plotting it, or how am I?
Yeah, how are you defining where the edge of the meniscus is?
There's different. So there's different ways you can plot it. So you could plot it as the zero equipotential line. You could plot it as the. You could plot it as here is the electron density, and of course, as the electron density gets higher and higher, your Debye length is so short, the meniscus is so it's pretty much where the electrons stop. You could do it. You could do it looking at the electric field. You could do it looking at the plasma potential. So. Yeah, the voltage. I quite like the meniscus being defined as the point where the voltage equals 0. Or sorry, the voltage is the same as the plasma electrode voltage. So if you take the plasma electrode equipotential and plot that, I'd call that the meniscus, I think. But it's a Debye length, and you've got this. I'm looking forward to studying this pre-sheath. There's a lot of theory that people have gone into it, and I'm actually a simple engineer. I'm actually an electrical engineer, so I don't understand the plasma physics really. I'm just doing this with brute force computational stuff, and I look forward to just seeing what I see. And I'll happily define the meniscus how anyone wants to define it, but I think it's a 0 volt equipotential, open to discussion.
Thank you so very much, Dan. We really appreciated this. That's all the
You're
time
welcome.
we have for questions today. We are going to take a brief break, and we will be back in about 7 minutes with our next talk. All right, thank you.
Thanks, everyone. Bye.